Okay guys, in this set of notes we're going to look specifically at reactions that take place in aqueous solutions. So we're going to be looking at double replacement reactions, and then in the next video single replacement reactions, and those are the two that we're going to focus on learning how to predict the products for. So in a double replacement reaction, like we talked about earlier, this is what happens when ions exchange between two compounds. Usually you look at the cations replacing each other, the anions replacing each other. You can look at it either way. But you have two aqueous compounds, and then in those solutions, the ions are replacing each other. And generally, you're going to get a precipitate, which is a solid that's produced during a chemical reaction in a solution. And here are two examples of precipitates being formed. That's what they look like. What we're going to focus on in this video, though, is how to predict the products of a double replacement reaction. So here's our example, and we're going to go through all the steps needed to predict the products. So first, we read through and look at our reactants. It says aqueous solutions of barium nitrate and aluminum sulfate react to form a precipitate. So we need to know what are the products, which one's the precipitate, things like that. What's our balanced equation? So the first thing we need to do is figure out what are the formulas for our reactants. And because these are both ionic, we have to take a look at their charges. Okay, so if we look at barium on the periodic table, then we see it has a charge of +2. Nitrate we know is NO3 with a charge of -1. And so when we put those two things together and write the formula, if barium is +2 and nitrate is -1, we're going to need two nitrates. So we write BaNO3 2, and it says an aqueous solution, okay? And it's reacting with aluminum sulfate. We look at the periodic table, aluminum has a charge of +3, sulfate has a charge of -2, so we're going to need two aluminums and three sulfates. So we write Al2SO4 3, and it is also aqueous. Okay, so that's the first step, writing the formulas for our two reactants. Okay, now the second step, we want to determine the ions. So we're kind of basically undoing what we just did, but we need to know what those reactants looked like. Now the reason we want to know the ions is because when these things are aqueous, they have broken apart into ions. So really we have all four of these ions moving around together with the water in the aqueous solution. So we said before that our barium has a charge of +2, so we're going to say Ba +2, and then we have nitrate -1, and then our aluminum ions have a charge of +3, and our sulfate ions have a charge of -2. Okay, so we want to see all of those individual ions as they are in solution. Okay, so what we're going to look at here now for our third step is to actually make the products. So, like we said before, our cations are going to replace each other. Okay, so what that means is the barium and the aluminum are going to switch. So the barium is going to come over here and react with the sulfate. So one of our products will now be barium sulfate. Barium is +2, sulfate is -2, so one of each. And then the aluminum is going to come over here and bond with the nitrate. Aluminum is +3, nitrate is -1, so we're going to need 3 nitrates. Okay, so those are the two products that are formed, okay? Now our next step is going to help us determine the precipitate. All right, so here's our rule, and this isn't a hard and fast rule, but it's a rule that's going to help us as we're determining the precipitate. When you have compounds with nitrate or compounds with an alkali metal as the cation, they're always soluble. They're going to be aqueous. So the other thing is going to be the precipitate. Now, those are not the only two rules, okay? You're going to see other things that are soluble. besides nitrates or alkali metal compounds, but those things are always soluble. So we know that they will never be the precipitate. So in our case here, if we look at this particular product, we know it has a nitrate in it, so we know that this one is the aqueous one, which means the other one, the barium sulfate, has to be our solid precipitate, okay? So that's how we're going to figure out our precipitate, is by looking at the one that's not nitrate and that's not an alkali metal. So because of the nitrate here, the barium sulfate is the precipitate. All right, now once we've figured out our precipitate, we need to balance our equation because as it stands, it's not balanced. So when we look at balancing, we want to make sure our nitrates are balanced. We have 3 over here, 2 over here. So we're going to have to put a 2 here and a 3 here. We have 3 bariums, 3 here, 3 sulfates, 2 aluminums, and now everything is balanced the way it is. All right, so let's look at a couple of terms that you might run across when we're predicting the products for these reactions. When we talk about aqueous solutions, there's always one or more dissolved substances in water. The aqueous part means in water. The solute is the stuff that's dissolved. The solvent is the most plentiful substance, which is going to be water when we use the term aqueous solution. So those are some of the terms you might run across there. Some possible solutes when you are looking at these double replacement reactions. Molecular compounds exist as whole molecules, okay, so we don't break them apart into ions because there are no ions. Compounds that produce hydrogen ions in aqueous solution are called acids, so sometimes we see hydrogen acting like a cation. And when ionic compounds dissolve in water, their ions separate in a process called dissociation, and we've seen that. That's why we write those aqueous ionic compounds separately as their ions. You can see a good picture here that shows the difference between an ionic compound, so our cations and our anions separate, versus a molecular compound like sugar. The molecules stay as whole molecules, they just separate from each other. Okay, and then we use the term electrolyte and non-electrolyte to mean conducts electricity, does not conduct electricity. So that when our two solutions that contain ions as solutes are combined, the ions might react. If they react, it's a double replacement reaction where they can produce either a solid precipitate like our example. We can also produce water and a gas. So it's not just necessarily a precipitate that's produced in these particular reactions. Okay. Okay, so now let's look at what's called a complete ionic equation. So when you have a complete ionic equation, it shows all of the particles in a solution as they actually exist. So aqueous ionic compounds, we have to show those split apart into ions. Solids stay together because they're still bonded. So when we have a balanced equation that, go back, where's my cursor? That looks like this, okay? These things that are aqueous, we have to actually show those as they really are, meaning we have to show them as cations and anions separate from each other. So here, this balanced equation now becomes a complete ionic equation where we have all of the things that are aqueous split apart into their ions. And then what that leads to is called a net ionic equation. And in a net ionic equation, you only include formulas of the particles that participate in the chemical reaction, which means there's some that don't, and we call those spectator ions, just like fans in the stands at a basketball game. The spectators are watching the game, okay? They're watching the reaction happen. They're not actually involved in the reaction, so they don't participate. We remove them from the complete ionic equation to get a net ionic equation. And the net ionic equation is solely showing us the chemistry that's happening. So in our example, we have our two sodiums here and here. They didn't do anything. They stayed the same. So the sodiums are they're spectator ions. We can get rid of them. The hydroxides and the coppers, those are the things that bonded to make the solid, so we can't get rid of those. But the chlorides, they didn't do anything either. They stayed as aqueous compounds. And this little aqueous should be over here. So our sodium ions and our chloride ions are the spectator ions. So to write a net ionic equation, we take them out and we write our net ionic equation, which we could abbreviate in IE, is going to be 2OH minus aqueous plus Cu plus 2 aqueous yields CuOH2, and that's going to be our solid precipitate. So that is the actual chemistry that's happening. These two things are bonding to make this one. The sodium was present, the chlorides were present, but they didn't participate in the actual chemical reaction. All right, now some double replacement reactions actually produce water molecules, and you don't see anything happening because when you make water, everything's in water already, so it doesn't look like there's a change. So here our net ionic equation would have the hydrogen ions and the hydroxide ions making water. So the bromides and the sodiums, those are going to be our spectator ions. You're not really going to see a reaction happening because you're making more water molecules that are already present. So you wouldn't see a precipitate in this particular case. Okay, so we want to write the chemical, complete, and net ionic equations for the reaction between aqueous solutions of barium nitrate and sodium carbonate. So those are going to be our two reactants. So we're going to come over here to a blank page and we're going to practice going through all of the steps. Okay, so we're going to start with our reactants, which were barium nitrate. Now you have to look at your charges. Barium is +2, nitrate is -1, and then sodium sulfate, sodium carbonate. Sodium is +1, carbonate is -2. So you need to be able to look at those charges and figure out your compounds, okay? So that was our first step, was to write our formula. Now we want to make them into ions. So +2 for barium, nitrate's -1, sodium is +1, and carbonate is -2, okay? Now, what happens in double replacement? The cations replace each other, right? So the barium is going to bond with the carbonate, and we get BaCO3 +2 -2. And then the sodium is going to bond with the nitrate, +1 -1. Okay, so those are our two products. We use our rules. What do we know? We know that compounds with nitrate and alkali metals are always soluble. Here's nitrate and alkali metal, so these are the aqueous ones. This one is the solid one, okay? Now, if we want to write the complete ionic equation, what do we need to do? Well, we have an aqueous thing over here that we need to write as ions. So Na+, NO3-. Those are both aqueous. Now we take out the spectators. Which things stayed ions? Well, the sodium ions stayed ions, the nitrate ions stayed ions, so those are our spectators, right? So what's left? We have the barium, the carbonate, and our solid precipitate. So our net ionic equation becomes barium ions plus carbonate ions yield solid barium carbonate. There we go, okay? So we end with the overall net ionic equation for that particular reaction. Okay, I'm just about out of time on this video, so we will finish and look at single replacement reactions in the next video.